So far, we've been seeing addition reactions to double bonds, but now we're going to see another type of reaction that we can do starting with a double bond, and that's ozonolysis. In an ozonolysis reaction, what happens is that there is a cleavage of the double bond and there is an oxidation, and we go from the alkene to carbonyl compounds. And because it cleaves right there, we're going to end up with two parts, two pieces, two molecules, right? So we're going to end up with this one right here that transforms into this ketone, and this one right here that transforms into that aldehyde. The reason why one is one ketone and the other one is an aldehyde is because this one right here, that molecule that results here, has an H. But if I had another R, like in the case of these ones, I would end up with another ketone. We're going to see so many other examples, and I'm going to point when you get a ketone or when you get an aldehyde. In this, so two reagents are needed. The first one is ozone, and the second one is the quenching part of the reaction. In this case, is dimethyl sulfide. And so this is what happens. We start with a double bond. Here you see where I'm showing all the atoms involved, and we're going to cleave right there and then end up with a carbonyl here and a carbonyl here. And again, just this is the exact same molecule that we had before, because here I have that H, I end up with an aldehyde, but in here, because I have two R groups, then I end up with a ketone. So that's the difference. Here, it's slightly different what's happening, and the reason is because this second step is different. So if we do a reductive workup, we're going to stop at the aldehyde, and that's it. That's what we're going to get. But if we do an oxidative workup, that's the quenching part, the second part of the reaction, we're not going to stop at the aldehyde, but we're going to get a carboxylic acid. You will see reductions and oxidations in organic chemistry too, and you may have seen this in the lab. So remember, reductive workup, we stop at the aldehyde. So in reductive workups, you can get ketones and aldehydes. And when we do the ozonolysis and we have an oxidative workup, you can get ketones or carboxylic acids, right? Sometimes you can get two ketones, but that will happen in both cases. But if you have a group that has one H, like this one right here, for the reductive workup, you will get the aldehyde, and for the oxidative workup, you'll get the carboxylic acid. So for ozone is this compound right here. It's very interesting because we cannot draw a resonance form that it's neutral. So these are the resonant forms of ozone. And this is the mechanism for ozonolysis. So you see here there is a first addition that forms this initial intermediate, and then the atoms rearrange with what you know from organic chemistry. You could follow the flow of electrons. So you see here we have a negatively charged ozone that attacks the carbonyl. You see that has the delta plus, it's the electrophile, and that will push the electrons to go and attack the other one, and that's how we end up with this 5-member ring ozonite, that it's actually the active species here, and that's the second intermediate. And then by using the reducing agent or the second part of the reaction, that, as you know, it could be oxidative or reducing, then we will get the two carbonyls in place. Now, this mechanism is interesting to see, is interesting that you can recognize it, but I won't ask you for it in the exam, right? But it's important that you see where this is coming from. And here I'm just showing you the same thing again with another example. So you see here we have that ozone that it's polarized, because even though it has three oxygens, right, one part of the molecule is going to have that negative charge, the other part is going to have that positive charge, and this is why these molecules are called 1,3. As I mentioned here, right, the 1,3 dipole reagents, because they have that dipole within the same molecule. Okay, so now that will react with the alkene, forming this intermediate, this 5-member ring intermediate that will rearrange to form the actual reactive species, is this 5-member ring. Then the second part is what's going to cleave this 5-member ring and give us the 2 carbonyls in place. And as I mentioned before, the ozones can be reduced, right, by using a reductive workup, and that will give us, remember, this is the aldehyde. So here you have one example. We have the double bond that is going to cleave right there. So we're going to end up with a carbonyl here and a carbonyl on this side. And so here, this carbonyl is a ketone. The other carbonyl is going to be formaldehyde because it has 2 H's. Or the ozonides, this intermediate, could be oxidized, and that's when we use H2O2. That is the oxidative workup. And so what's going to happen in this example right here is we're going to cleave that double bond, and we're going to end up with a ketone, with a carbonyl on each side, right? So in this case, we have a ketone. On the other side is going to be a carboxylic acid. Remember, it's not going to be the aldehyde, it's going to go all the way to the carboxylic acid because we're using oxidative workup. So here we have this example right here. We have ozone, and then the second molecule that sometimes you're gonna see DMS or dimethyl sulfoxide is dimethyl sulfide, sorry. And that is this one right here, right, that we saw at the beginning. So this is a reductive workup. So this molecule right here is this one, or sometimes you're also going to see it like this. For the reductive workup, remember, you can use zinc or these molecules, and the 3 of them mean the same. Okay, so now if we go back to our example, we know that we have a reductive workup, which means is that we're going to end up with a ketone and an aldehyde, or 2 ketones or 2 aldehydes. How do we know what we're going to get? Okay, so we have the double bond that we're going to break right there. And so you see here, this part of the double bond has 1 R, and here it has 1 H. At the bottom part, I have 1 R and another R. So the bottom part is going to give me a ketone, because remember, ketones are going to look like this with 2 R's. They don't necessarily have to be the same, so it can be R1 and R2. And the top part, because of that hydrogen right there, is going to give me an aldehyde, right? So I know that with this molecule, because it has that H, I'm going to get an aldehyde, and at the bottom, I'm going to get a ketone. And the reason why the top part is going to be an aldehyde and it's not going to be a carboxylic acid is because of these conditions here, the reductive workup. Okay, so the first step is going to be cleaved with the ozone, and the second part is going to be that workup, that reductive workup. Okay, so the best part, the best way for me to show you how to do this is you simply kind of expand the molecule a little bit, and you simply put 2 carbonyls right there. And so here you have the H, and at the bottom I'm going to have the methyl. And the last thing I have to show here is the methyl, right? The stereochemistry is not lost there. And if you want to draw this molecule in a different way, what you could do now is do 1, 2, 3, 4, 5, and 6. And remember, this numbering has absolutely nothing to do with how to name this molecule. It's just for me to redraw it. So 1, 2, 3, 4, 5, and 6. And so at position 6 is where the aldehyde is. At position 5, I'm going to have that methyl, right? That methyl that it's pointing towards me, so that's going to stay like that. And then at position 2, I'm going to have another carbonyl, right? So this is another way of transforming this cyclic molecule into the, so actually this cyclic molecule expanded into a more linear one. Another conditions that do the exact same thing is potassium permanganate, or permanganate, but we usually see that as potassium, right? That's the counter ion permanganate. So you're often going to see KMnO4 as the species that we use. And the result is the exact same thing. What happens is that this bond is going to be cleaved right there. The only difference here is that by using potassium permanganate warm, we're never going to get aldehydes. We're always going to go all the way to the carboxylic acid, right? So we're only going to get carboxylic acids in this type of cleavage, right? We can get ketones and carboxylic acids, but we won't get aldehydes. And right here, I have the comparison of using potassium permanganate and using ozone. So by using potassium permanganate, you see this double bond right here is going to be cleaved. And remember, we are going to end up with a carbonyl here and a carbonyl here. And what you expect from an ozonolysis and the reductive conditions is that you have the aldehyde right here. But in potassium permanganate, that doesn't happen. What happens is that it goes all the way to the carboxylic acid right here. Well, the carboxylate that then gets protonated, but it goes to the carboxylic acid. In ozone, when we use these DMS, that's our reductive conditions, we can isolate the aldehydes. We can stop at the aldehydes. The other option that I haven't said here is that we could have O3 as the first step, and 2 have H2O2. And then if that happens, we will get the same molecule that we will get with potassium permanganate. All right, so there are 3 possibilities of ozonolysis of that oxidative cleavage. The first one is using potassium permanganate that goes all the way to carboxylic acids. And then for this oxidative cleavage of the using ozone, we have 2 options, one in where we can isolate aldehydes, and the second one where we will end up having carboxylic acids.